Boa noite a todos. A Biblioteca Pública e Arquivo Regional Luís da Silva Ribeiro, em nome da Sra. Diretora Cláudia Cardoso, que hoje não é possível estar aqui hoje, agradece a vossa presença e é com muito gosto que acolhe a segunda semana do Universo. Desde os primórdios dos tempos que o Universo suscitou curiosidade e fez despertar a imaginação nos seres humanos. Inspirou os escritores, os filósofos, os poetas e os cientistas. E é nomeadamente na área da ciência da astronomia que os seres humanos ganham conhecimento, um conhecimento científico, rigoroso e objetivo. Esta segunda semana do Universo vai proporcionar várias iniciativas. Hoje à tarde decorreu a atividade da construção de telescópios direcionada mais para um público jovem e agora iniciamos o ciclo de palestras, que terá continuidade nos dias 8 e 10. Temos também uma exposição de fotografia, um céu açoriano entre brumas e luminárias, que ficará até ao final do mês. A Biblioteca também selecionou um conjunto de obras que abordam esta temática da astronomia, que poderão consultar ou requisitar para empréstimo. No final de cada palestra, caso as condições meteorológicas o permitem, haverá as observações noturnas. Bem, eu penso que são boas razões, bons motivos para que fiquem connosco e visitem a Biblioteca.
So, hello and welcome to the second Universe Week. I'm Carlos Martins from the Center of Astrophysics of the University of Porto. As you heard, this is one of a number of events that we have throughout this week. They are part of a PhD school that us, the University of Porto and the University of the Azores and ESO are organizing here. So this is the fourth edition. And as part of our social responsibility as scientists, we try to organize a number of other activities for schools and the general public and so on. I'm very happy to see in the audience people that are also participating in some of these other activities. So this is one of 4 public talks that we have. Due to COVID, the in-person attendance is limited, but we are also webcasting the talks, so people not only in the Azores, but all over the world, essentially, can listen to the talks. So tonight we have Paulo Padovani. Paulo is from Italy. He studied in Padova, and for many years he's been working at the European Southern Observatory, and among his different tasks, he's part of the science office of the Extremely Large Telescope, which is the next generation optical and infrared spectrograph that ESO is building, and that will be operational a few years from now. Hopefully, some people in the room will have the chance to use it for many years. So with that, I'll hand over to Paulo, who will tell us how one goes from the Big Bang to us in 1 hour. Paulo, over to you.
Thanks, Carlos. Boa noite. That's my Portuguese. Good evening, everybody here and at home. My kids are watching this, by the way, from the UK. I'm really, really happy to be here for various reasons. One is that I love to talk about astronomy to non-astronomers. I do it regularly. And the other one is that I've been doing it for 2 years, for reasons that we all know. So it's the first time in a couple of years that actually I managed to give a public talk. So I'm really, really pleased that things are going back to normal. So tonight I'm going to tell you a story. We humans are programmed to listen to stories. So this is what I'm going to do tonight. So this is not any story. It's the mother of all stories. It's our story. Without this story, there would be nobody here today to listen or to tell. It's a story of how we got from nothing to us in 1 hour. It's a very complex story. I made it very simple. Well, sorry, I made it simpler than it is. But it will require your full attention and concentration for 1 hour. Because, as I said, it's very complex. Before we start, I have to say something. Everything in the universe has to do with physics. Whether you like it or not, that's the way it is. The sun is a gigantic power plant, transforming hydrogen into helium all the time, as I'll say later. Driving a car, it's to do with physics. Playing tennis, you have to do with gravitation. You have to do with, sorry, this is not working properly. The friction of the air, which is going to stop your ball. Light, the torque of your elbow. And the language of physics is math. Galileo Galilei realized this 400 years ago. L'universo è scritto in lingua matematica. The universe is written in mathematical language. So today, I had to translate from mathematics to a language that is a common language, can be understood by people who are not scientists. And in the process, though, I kept some numbers. I'm going to give you times, distances, masses, and that's so that you have an idea of the scales we're talking about. So the story today is how we got from here, the Big Bang, to us, meaning beings on a planet close to a normal star in a normal galaxy in 13.8 billion years. So let's start from t equals 0. So up there at the right, you see the time. This is 0, okay? Do you see anything there? No, because there is nothing to see. At the beginning, there is absolutely nothing. You can't even imagine, it's nothing. There is no time, there is no space. There is no here, there is no there. There is absolutely nothing. But every now and then, out of nothing, a fluctuation, a quantum fluctuation comes, and then it goes. And it keeps happening. And at a certain time, one of these fluctuations stays. And that's us. The seed of everything we know today, it's in this fluctuation, which is smaller than, billions of times smaller than the size of an atom. It's tiny, but the seeds of everything is in that fluctuation. This is t equals 0. Unfortunately, we don't know. Physics doesn't tell us what happens at t equals 0, because the closer we can get to the Big Bang is this value. It's 0 followed by 42 zeros and 1, which in notation in science we say 10 to the minus 43 seconds. It's a very, very small number. But before this time, we don't know what happens because we don't know the physics. To do this, to understand this, we need to merge gravitation with quantum mechanics, and we can't do it now. So we know what happens after this time. Before then, sorry, the format has been changed, transformed to the computer, it doesn't matter. So we only know after this time. This fluctuation is extremely high. We're talking about billions of billions of billions of degrees, okay? The sun is about 5 million degrees. This is really, really hot. And it's, as I said, smallest than anything you can think of. It's really, really tiny. So tiny and very, very hot. How do we know what's happening? Because we know physics, and the two things which are actually ruling what's going on here are two things. One is the mass-energy equivalence, the famous E equal mc squared equation of Einstein, the most famous but least understood equation in humanity. It simply says that you can go from mass to energy and energy to mass, matter to radiation, radiation to matter. The details are not relevant. The second rule is that you have to conserve the charge. If you produce a positive charge, you need to produce a negative charge at the same time, because the sum has to be 0. Whenever people listen to conferences, it sounds like we know everything. That's not true. So in this conference, I'm going to show you open problem where there are problems which are not solved. And this is one. We don't know what happened. We don't know where this fluctuation came from. We don't know the physics before this time. And every now and then you see this thing coming out. These are things which we don't know. And I think it's good that the public knows that we don't know everything. Far from it. Okay, so you have this, it's called primordial soup. You have a mess. It looks like a mess. Things are bumping into each other, particles are being produced, particles are being killed, and all that. As I said, there are two things going on. One is the following. It's called pair production. You have radiation, light, two photons. Photons are the carrier of light, light we see. They smash against each other, and they produce two particles. But they have to be, remember, one has to be positive, one negative. So a particle and antiparticle, matter and antimatter, a proton and an antiproton. An antiproton is like a proton with a negative charge. Okay. I don't know what happened, sorry. So here we have radiation turning into matter, so energy becoming mass. But the opposite happens. When you produce a particle and antiparticle, when they touch each other, they annihilate, and they produce light. So you have all these two opposite things happening. Light becoming matter, and matter becoming light, all the time. And it's in equilibrium. It's happening constantly. But the point is the following. The higher the temperature of the universe, the higher the energy of this radiation, the larger is the mass of the particles that you can create. So the hotter you are, the bigger are the particles you can create. But the universe is expanding. This fluctuation, which was tiny, is now expanding really, really fast. It's becoming big. The universe is becoming bigger, and when something gets from small to big, it gets colder. So the universe is becoming bigger and colder at the same time. So look at the time now. Now we're at 0.1 milliseconds. The universe is much colder than before. It's only 10 trillion degrees, 10,000 billion degrees. At this temperature, the radiation is not energetic enough to keep creating protons and antiprotons. So the creation of protons and antiprotons stop. You're done. But then, there are zillions of protons and antiprotons pairs in the universe because they've been created before. And every time they touch each other, they die. But since particles are created in pairs, all particles should annihilate and get destroyed. And then at the end of the day, there should be no matter left, because every particle is going to kill each other with the antiparticle, producing radiation. But this is not true. Every time I think about this or say this, I get the shivers. Every billion pairs, there is a single unpaired proton. So you have zillions of pairs. Every billion pair, one proton is by itself. He has nobody to annihilate with. So after this period, 0.1 milliseconds, you're only left with the protons. Because every billion pairs, there was an extra proton. Nobody knows why, because according to the laws of physics, it should not happen. This is called the matter-antimatter asymmetry, and it's an open problem. Without this asymmetry, there will be nobody here today, because every proton would have been created with an antiproton, and then it will be destroyed itself when the creation of protons and antiprotons stops. So it's only thanks to this that there is matter in the universe. Without this asymmetry, there will be no matter, only light in the universe. So it's a huge mystery. Now, time goes on, 100 seconds, the same thing happens. Now the universe is only 5 billion degrees, and it doesn't have the energy to create electrons and anti-electrons. So this creation stops, but, as before, every billion electron-anti-electron pairs, there is a single unpaired electron, and so you're left only with electrons. So, after all these messy things, the universe is only 100 seconds old. We are left with protons, neutrons, which I'll mention in a minute, electrons, and light, and neutrinos, but we don't care now. So now the universe is much simpler than before. Matter, that we know, and radiation. The universe now starts creating atoms. What's an atom? You're all familiar with it, I guess. So matter is made up of elements, and atoms are made up of a nucleus, which includes protons and neutrons. This is an atom of helium. It includes 2 protons and 2 neutrons, and there are 2 electrons moving around in a cloud. The important feature of an element is the number of protons. Helium has 2 protons. This is the so-called periodic table. This is all the elements we know. And as you can see, the number here, 1, 2, is the number of protons. So hydrogen has 1 proton in the nucleus, helium has 2, lithium has 3, beryllium has 4, carbon has 6, and so forth. Now look at the time. Now the time is between 3 and 20 minutes. The universe is trying to make atomic nuclei. How? All these protons and neutrons which are around are very, very hot. They collide with each other. A proton and a neutron will collide and will produce a nucleus of deuterium. And the same will happen to another pair, and you'll have 2 nuclei of deuterium, which will smash and produce helium. 2 protons, 1 neutron, and one neutron, 1 free neutron. Until now, there was only hydrogen in the universe. A proton is the nucleus of hydrogen. Now we have the first element apart from hydrogen, which is helium. Okay? There are many, many elements. Until now, there was only 1, hydrogen. This is the second one created by the universe. Why? Because to convince 2 atoms of 2 nuclei of deuterium to get smashed together, you need to have a very, very hot universe, because these 2 protons will tend to repel each other. Positive charges are going to repel each other. So you need to be really, really convincing and very, very hot to convince them to fuse. Only a hot universe can manage to produce atoms, in this case, helium. Elements are atoms with electrons around. So you have a nucleus, and you have to have electrons. Look at the time now. Before, we were talking about 3 to 20 minutes. To form elements, you need to be able to have the electrons bound to the nucleus. Before this time, the universe was too hot. The elements were trying to form, but the radiation was smashing, taking away the electrons from the atoms, and so there were no elements. Only nuclei, no proton, neutrons, and electrons. Now the temperature is less than 3,000 degrees, and the first elements can actually be formed. But now the universe is too cold. So it only managed to produce a bit of helium, a bit of lithium and beryllium. So at this point in time, after 300,000 years, we have a universe made of light, 3/4 hydrogen, 1/4 helium, and a sprinkle of lithium and beryllium. That's it. Only 4 elements. We don't go very far with this. We are made of oxygen, carbon, phosphorus, iron, whatever. So at this point in time, life cannot be supported by the universe. Okay? How do we get the other elements which are fundamental for our bodies? It's all thanks to gravity. I haven't mentioned gravity so far, because until this point, gravity was completely irrelevant. Why? When you have free charges, if you calculate the repulsion that 2 protons have against each other, because they are positively charged, and you compare with the gravitational attraction that they have because they are heavy, the ratio is huge. It's 1 followed by 36 zeros. So gravity, until you have free charges, is completely irrelevant. Once you have elements, elements are neutral, because the protons are positive, the electrons are negative, an element is neutral. Now the universe is neutral, and gravity starts to kick in. Look at the time now, 380,000 years. So, imagine a universe made out of, as I said, hydrogen, helium, other couple of elements, lithium and beryllium. But this universe is not homogeneous. This is a map of the temperature of the universe 380,000 years ago. Redder points are warmer and bluer points are cooler. The universe does not have the same temperature, which means that the universe does not have the same density. It's not like a sand, like a beach, where the sand is distributed evenly. There are bits and pieces, locations where there is more matter, and locations where there is less matter. We don't know why. And what happens? Imagine you have a very, very thin sheet of rubber, and then you put pebbles on it. The pebbles will just start making these holes. And a pebble, a big pebble, will start attracting nearby pebbles. So these condensations will grow with time. The same thing happens in the universe. The regions which are denser start to attract matter from outside, and they become denser and denser and denser. But at the same time, remember, the universe is expanding. So you have gravity trying to pull things, and the universe trying to take things away. So it's a rush against time. Gravity is trying to build things, and the universe is trying to destroy them. Look at the time now. We went from 380,000 to 200 million years in one go. Why? Because at this time, the first stars are born. Why do we know the time? Because to build a star, you need 5 million degrees. Now, the universe at this point is very, very cold. It's about minus 216 Celsius already. So it cooled down a lot. How do you get 5 million degrees? Gravity. The condensation that I was mentioning earlier, they start to make things getting smaller and more compact. When you squeeze something together, like gas, it gets hot. So these condensations, by pulling matter from the edges to the center, this matter gets hotter and hotter until it reaches 5 million degrees, and then a star is born. The first star is born. What is this? Open problem, because we haven't seen them. Nobody has seen the first stars yet. We know they're there. We have some idea about how they are, but nobody has seen them so far. What is a star? My favorite definition is that it's a body which is in perfect equilibrium. Gravity is trying to pull the edges of the star towards the center, but the pressure of the hot stuff inside the star is trying to push it away. The radius of a star is exactly where the two forces cancel out, gravity and pressure. So a star is a body which is in perfect equilibrium until things don't change. So you have, as I said, gravity trying to pull things inside and pressure trying to pull things away. Sorry. How does a star work? Humankind took a long time to understand this. You have 4 hydrogen atoms, like in the beginning of the universe, okay, where you are fusing deuterium to get helium. Here you take 4 protons, which are hydrogen atoms, and they become an atom of helium. And by doing this, they produce energy. To be more specific, oh, sorry, I don't know what. I have to give up with this. So, to be more precise, the sun converts 600 million tons of hydrogen into 596 million tons of helium every second. That's a lot of conversion. We're missing 4 million tons. Why? Because 4 atoms of hydrogen weigh slightly less than an atom of helium, and the difference in mass gets released into energy. So it's nuclear fusion which is powering the sun. Hydrogen becoming helium and producing energy. Same time, first galaxies. What are galaxies? Galaxies are ensembles of many, many stars. Our galaxy contains about 200 billion stars. So as you can see, there are various types of galaxies, but the main question is, do stars form first and then they get attracted to each other by gravity and become galaxies, or do condensations first form galaxies and then stars get lit up? We don't know. We don't know which one comes first, if stars or galaxies. It's another open problem. We do know, we have observed one of the most distant galaxies. Look at the time now. The universe has become 400 million years old, and this is the most distant galaxy ever observed. It's this little speckle there, which is zoomed in here. This galaxy is the most distant one ever observed when the universe was 400 million years old. But how do we know that? How can we go back in time? So if the universe is 13.8 billion years now, we have to go back in time 13.4 billion years to go back to the first galaxy. But that's because the universe is a gigantic time machine. Why? Because the speed of light, although it's very high, it's finite. It's about 300,000 kilometers per second. The light from people sitting at the edge of the room doesn't come to me instantaneously. It takes about a few microseconds to come to me, a few millionth of a second. If you say, okay, it's irrelevant, true. But the sun, we see as it was 8.3 minutes ago. So if the sun died now, we will know in 8.3 minutes. Well, now we will know because it's night. But during the day, it would take 8.3 minutes to come to us the fact that the sun has disappeared. Saturn, the light takes about 80 minutes to come to us, which is very relevant if you're sending a spaceship to Saturn and need to turn on the engine at the right time. The signal has to leave 80 minutes before the engine has to turn on, otherwise you're done. The signal will not get there in time. The closest star to us, Proxima Centauri, is 4 years and 3 months ago. Sorry, we see the light from the star the way it was 4 years and 3 months ago. And from Andromeda, which is the biggest spiral galaxy close to us, the delay is 2.5 million years. So imagine now there is an astronomer on Andromeda with a big telescope looking at us now. He would see our ancestors because he would see Earth the way it was 2.5 million years ago because of this travel time. So now we have this universe after 400 million years with stars and galaxies, but we still have the problem of the elements. We only have hydrogen, helium, lithium, and beryllium. We are missing all the ones which make us, for example. Where do they come from? So this is the list of the most common elements in the human body, in order, okay? The first 6 make up 99% of our weight. Oxygen, carbon, hydrogen, nitrogen, calcium, and phosphorus. But you need all the other ones as well, otherwise we'll be dead. You need potassium, magnesium, also iron, and so forth. So, but the first 6 is 99%. None of them, apart from hydrogen, is around. So we still don't know where these elements are coming from. The answer is the stars. Stars, like everything else in the universe, are born. This is the Orion Nebula, which is a nebula where actually stars are being born as we speak. It's in the Orion constellation, which can be seen from the northern hemisphere, even tonight, at 4 o'clock, you go out, you see this constellation, and that's the nebula. Stars are born all the time, and they grow up, they evolve. Why? Because the sun, or any other star, is burning hydrogen into helium. But like any other thing, like a car, sooner or later you'll end up running out of hydrogen. So what happens? Remember, the star was in equilibrium between gravity and the pressure of the hot stuff. If the star dies because it doesn't have any more fuel, gravity will start to take over. And so the stars start contracting, and contracting, and contracting. And what happens when you contract a star with something? It gets hotter. If you have a balloon full of air and you squash it, the air inside will get warmer. So the star becomes smaller and hotter. And now you start burning other stuff. Until now you are burning hydrogen into helium, you run out of hydrogen, and now you start burning stuff, and then the star expands again and becomes a supergiant, a red supergiant in this case. So, remember, we've run out of hydrogen because we created helium. And now we have to burn helium. So, all you need to do is to convince 2 atoms of helium to merge and become an atom of beryllium, to merge with another atom of helium, and you go from helium to carbon. Carbon is a nucleus with 6 protons and 6 neutrons, so carbon 12, that's the 12 there. So, but here, while for the fusion of hydrogen into helium, you had to convince 4 protons to merge, now you have 6 protons. So the temperature you need, it's much higher. Before, 5 million degrees were enough. Now here, you need 100 million degrees. So to burn hydrogen into helium was one thing. To burn helium into carbon, it's a much tougher thing. You need to have a much hotter star. And then things goes on. Now, helium will run out, and you'll have left with carbon, but then you have carbon plus helium giving you oxygen, oxygen plus helium giving you neon, carbon and carbon producing magnesium, and you have the idea. So you keep producing heavier and heavier elements until you get around iron. Every time you do this, you have to have a hotter star. So the temperature of these reactions increases. And at the end of the day, the star is going to be like a sort of an anion structure. The heavier elements at the center, and then the further outside you go, you have the lighter elements. So hydrogen is going to be outside, helium slightly closer to the center, carbon, oxygen, blah, 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 all the way down to roughly iron. But when you get to iron, then things get sort of strange. Until now, remember, stars were producing energy by fusing these elements. When you get to iron, and you start fusing iron, you need energy. So the star cannot keep itself supported anymore. And this happens. Okay. The star explodes. In a few seconds, the star cannot support each other, it collapses to the center, bounces back, and throws all the elements it produces into space. And makes these beautiful things which are called supernova remnants. The star has become a supernova. A supernova is a star which is basically stopped supporting itself by producing energy, and it collapses towards the center and throws everything that it produced over billions of years into space. And you're left with this. This is a real picture. This is the Crab Nebula. It's the nebula of a supernova which exploded in the year 1054 in the constellation of the Crab. And this is actually what's left of a star. At the center of the star, after this explosion, you have two options. If what's left at the center has a mass which is smaller than twice the mass of the Sun, which, by the way, has a mass of 2 followed by 30 kilograms. So if this mass is less than 2 solar masses, then you have a neutron star, which I describe in a minute. If you have a mass which is above this, you have a black hole, and I have no time to discuss it. I can answer a question later, but at this point, we care only about the neutron stars. So what's a neutron star? So imagine the star has collapsed. It has thrown out most of its elements into space, but there is something, a core at the center. This core is so dense that, remember the elements. The elements, you have protons and neutrons at the center, electrons are around. When you have a neutron star, the electrons and the protons merge, and they become neutrons, plus neutrinos. So you don't have nuclei anymore. Everything has become neutrons. And at this point, the only thing which keeps the star from collapsing is the pressure of the neutrons which are squashed together. So gravity would like to keep squeezing the star, but the neutrons are so tightly packed that gravity cannot make it. A neutron star is something so dense that a cubic centimeter, something this big, weighs about 10 billion kilos. It's denser than an atom of a nucleus, because matter has been really, really squashed to death. And the only way it doesn't become a black hole is because neutrons are basically there fighting gravity. If the mass is bigger than 2 solar masses, gravity wins, and the whole thing collapses. So, now I can tell you where the elements come from. So this is now the usual periodic table, and this is a variation where now the elements are color-coded, and you see where they're coming from. So, remember, hydrogen was there, helium is created in the universe, early universe, lithium and some beryllium, which is not even there. Supernovae make all the green and sort of light blue stuff, up to rubidium. Okay? Nothing beyond that. Beyond that, the heavy elements are neutron stars. 2 neutron stars colliding. Okay, you might say, I don't care. Well, here we have, in this region, we have gold, we have platinum, we have iodine. Iodine is important for our it's a growth hormone. So basically, without iodine, we couldn't grow. So iodine is produced in the merger of neutron stars. So what happens? You have, I said almost solved because almost everybody agree now on where the elements are coming from. This was not solved until a few years ago. So you have 2 neutron stars. They get close to each other. They spin around. And then they actually become one. And all the neutrons which were there, with the little iron and other elements which were there, produce all the heavy elements, the ones heavier than rubidium, the ones which we have in our body, but also, as you'll see in a minute, are fundamental for us as well. Now, this merger, apart from producing the elements, produces also something which is called gravitational waves. Which were predicted by Einstein 100 years ago, and actually were detected in 2016, and these 3 people who led the collaboration actually got the Nobel Prize for it. But this is another story. At this point, we care about neutron star mergers because they produce the heavy elements. So why do we care? This is now another version of the periodic table. It shows you the metals in a cell phone. Everybody has a cell phone, right? So you can see there are many elements above rubidium. All these elements from rubidium onwards have been produced by the merging of two neutron stars. So without these neutron star mergers, there would be no cell phones. I don't know if that's a good thing or a bad thing, but we could discuss it. But this is the main point. Anything heavier than rubidium is created by the merger of two neutron stars. Okay, now let's fast forward. Look at the time now, 9.3 billion years. A special star is born. The star is born in a spiral galaxy, about 3/4 away from the center, close to a spiral arm, and the star is called the Sun. The Sun is our own star. And it was born when the universe was about 9.3 billion years old. The Sun, of course, has planets around. So when the Sun was born, also the solar system was born. And this is a very, very complicated story, which is still not solved. The idea you have this nebula made of some material, which was moving a little bit there. A supernova explodes nearby and starts compressing this nebula. The nebula becomes smaller and starts rotating faster. It forms into a disk and planets get born. I made you a very, very complicated story, which we still don't know how it works. Very, very simple. Why does this nebula, which was moving slowly, start moving faster when it gets smaller? It's the same principle as this ice skater. She's rotating slowly when the arms are extended, but then she closes the arms, and then she rotates fast. This is called conservation of angular momentum. The same thing happens in the primordial solar system. These are real pictures of solar systems being born, and these dark rings are planets sweeping these disks and cleaning them up. Planets being formed in these these solar systems, actually, which are in this protoplanetary stage. As I said, this is a very complicated thing. We still don't know exactly how the solar system actually was created, but it was. And so here we are with the Sun, our 8 planets, the Earth is there, and our planet was created that way. The beginning of the solar system was very complicated, very difficult place. We know that the moon was created when a planet the size of Mars collided with the Earth and removed a chunk of it, and this became the moon. But then things stabilized, and then you get the solar system that we know now. Now, our galaxy includes about 200 billion stars. This Andromeda galaxy, which is the closest spiral to us, has about 1 trillion stars, 1,000 billion stars. And there are about 2 trillion galaxies in the universe. So there are many possible solar systems. Are they there? The answer is yes. Until 1995, we knew 9 planets in the universe, our own. Now we know about 5,000. This is the number of planets discovered as a function of time. And these are extrasolar planets, planets orbiting other stars. We know about 5,000, okay? So that's a large number. There are many stars in the galaxy, and all of these stars have planets rotating around them. And another Nobel Prize in 2019 went to these guys, Michel Mayor and Didier Queloz. They were the first one to discover an exoplanet orbiting a star similar to the Sun. Before this time, 1995, as I said, we knew 9 planets in the universe. Now we know 5,000, and the number is rising. Of course, when we talk about planets, we think about life. And so we, astronomers, have invented this thing which is called the habitable zone, which is the zone where we can have liquid water. Why? Because we know one example of life in the universe, which is us, and this life needs liquid water. So in this graph, you see the mass of the star, and this here the distance of the star, and here this is the solar system. Okay, so this is Mercury, Venus, Earth, Mars, and Jupiter, and this is the habitable zone for the Sun. And as you can see, it goes from Venus to Mars. So clearly, habitable does not mean inhabited. So there could be liquid water, but in many cases there isn't. If the Sun is smaller than the Sun, then the habitable zone gets closer, and this is a real star with real planets, one of them being in the habitable zone of the star. As you can imagine, astronomers love to find planets in habitable zone, because there you could think that there is life. And this is, one of the major big questions of humankind. Are we alone? Is there other life, aliens, and so forth? So this plot, don't forget about all the details, shows you all these names are planets which are moving in the habitable zone or their star. We know many. These planets are actually sort of Earth-like, similar mass, in conditions which are favorable to life. And the numbers are that about 1 star out of 10 has an Earth-like planet. Now, as I said, the galaxy is about 200 billion stars, so we're talking about 20 billion Earths around there. That's a huge number. As I said earlier, though, habitable is not enough. Look at Venus. This is Venus from space. Do you see anything? It has a very thick atmosphere. With radar, you can see the ground, and there is not much. Venus is really a very bad place. It has a CO2 atmosphere of 150 degrees and the ground pressure of 93 atmospheres. Lead is liquid on Venus. Okay, so it's really not very habitable. Mars, again, it's in the habitable zone. Mars has the other problem. It has no atmosphere. By the way, Venus, we know that there was water on Venus 3 billion years ago. Mars, we know that there was water billion years ago. The atmosphere is very rarefied. It goes down to minus 80 degrees. And in some cases, it goes above 0 at the equator, for example. And these are ancient rivers. There was liquid water on Mars. It's gone. It's totally gone. Why? We have some ideas. The Sun keeps throwing out particles to us and to Mars. But the Earth has a magnetic field which shields us from these particles. Mars doesn't have that. So with time, these particles have been eroding and basically throwing away the atmosphere, and so water is being evaporating. Open problem in the sense that we still don't know habitable, what does it mean? How do you get inhabited, and so forth. Okay, now, I'm taking a poll. I have 7 more slides on the future. I told you that I was going to take it from the Big Bang to us, and I did it. Now I have 7 slides on the near and very far future. We're talking about billions of years. So, show of hands. Who want? I can skip them and go to the end, or I can show the 7 slides. So who wants to show the 7 slides? Raise your hand now. Okay. Who wants to stop here? Okay, wow, okay. You want to go. 7 minutes. So, we are here now on a lovely planet, which is getting warmer, but this is nothing compared to what's in store. So, that's because the luminosity of the sun, the amount of energy which is radiating, is not constant. It's this red light, red line. It's going up with time. Not much. It's going up by 1% every 100 million years. Who cares? Well, in 1.1 billion years, there was going to be no water on Earth. The temperature of the sun is going to be so high that all the oceans are going to be evaporated. So forget global warming. This is really warming, okay? So no water left. But there is worse to come. 5 billion years from now. Remember the story? The sun is burning hydrogen, okay? All the time. But with time, you're out of fuel. And what happens? When you're out of fuel, the star dies, it stops producing energy, it contracts, it becomes hotter, and then it starts fusing helium into carbon. It becomes much bigger, and if you are a planet sitting there, woof, you're burnt to death. So in 5 billion years from now, Mercury, Venus, and probably the Earth will just be right there, are going to be engulfed by the sun, gone completely. And what about the sun? Remember the supernova, so the star fusing iron and other elements and not being able to support it as well. The splendid explosive death only happens for 1% of the stars, the big ones. Most stars, like the sun, die very, very slowly. They run out of helium. They would like to start burning carbon. They can't. They're too small. So after helium burning, the sun is dead. It expels some material which forms these beautiful things, and this is what's left. It becomes a white dwarf, a star which becomes smaller and very, very cold, for astronomical standards, of course, and it dies off, not with a bang, but very, very slowly. So 99% of stars die this way. Only the big ones, the 1% which is bigger than 8 times the mass of the sun, dies as supernovas. Now, what about the habitable zone? This is interesting. So right now, as we said earlier, the way the sun is now, it goes from Venus to Mars. But when the star becomes a red supergiant, becomes bigger, 2 things happen. It loses half of its mass, which means the planets expand, move away. Jupiter goes from here to there. If the sun is less big, then there is less gravity, and you actually move away. But the habitable zone now is around Jupiter and Saturn. So if you are sitting on Io, Callisto, Europa, which are these satellites of Jupiter, which right now are very, very cold, in 5 billion years, you'll be having liquid water. So if we are clever, by then, we might be moving to Europa, and we'll be fine because we'll have running water and oceans and all that. So there is hope for mankind to be able to move and leave Earth. So, as I said, the sun started from a nebula. Probably its creation was triggered by a supernova nearby. Then it stayed the same for about, well, it will stay the same for about 10 billion years, we are actually halfway through. So the sun is a middle-aged star, 5 billion years. In another 5 billion years, we'll become a red supergiant, destroying Mercury, Venus, and possibly the Earth. And then it'll die off as a white dwarf. Okay, now comes the real fun. Fast forward now to 100,000 billion years. Okay, I remind you that the universe now is 13.8 billion years old. This is 100,000 billion years. It's an amazing number even for us astronomers, okay? So, the title of this is The End of Everything. Why? Remember the story, you're burning hydrogen, then you're burning helium, then you die. If you're big, you throw out elements, you create new stars, but you're still burning. There's a lot of matter in the universe, but everything has a limit. In 100,000 billion years, there is going to be no fuel left in the universe. So, this is the sky in 100,000 billion years. Do you see anything? We are back to square one. We started black at the beginning of the universe, and now we end up black. There are no more stars. All stars are dead. All galaxies are dead because they've dissipated. There are some black holes every now and then merging, neutron stars merging, giving you a flash, but less and less. That's it. So no work for astronomers in 100,000 billion years because there's going to be nothing to observe. Everything is going to be dead, completely, utterly dead. Okay, we made it. So we went from black to black, in a way. So black where there was nothing because there was nothing, and black because everything else, everything is dead. In 1 hour, as I said. And I think it's an amazing journey. It's an amazing thing. But you know what is the most amazing thing? That a bunch of hydrogen, oxygen, carbon, potassium, phosphorus, like us, after 13.8 billion years, managed to turn back and understand where we're coming from. I think that's the most amazing thing of all. That the bunch of atoms created by the Big Bang in stars at billions of degrees get put together, they acquire some power, intelligence, they turn back and they say, I come from there. I think that's absolutely amazing. So, we talked about a lot of things. I listed them here. Quantum mechanics, primordial nucleosynthesis, star formation, nuclear fusion. And I told you at the beginning I was going to discuss all this. Half of you were probably left because they look very complicated. But I tried to make them simple. And as I said, there are many things that we don't know. And so I hope you understood that there are things we don't know. But if mankind is proud, supposed to be proud, because we actually understand where we're coming from, you should be proud because you managed to follow all this stuff in 1 hour. Thank you very much.
Thank you very much. We have time for some questions.
We have a Facebook question for you, Paulo. So the question is, do you think there is any chance we will discover evidence of alien life within our lifetimes?
That's, of course, I get asked that all the time. Alien life? Okay, the telescope we are building, that Carlos mentioned before, one of the things it's supposed to do is to look at the atmospheres of extrasolar planets. So if you have a planet with an atmosphere with a lot of oxygen, for example, like us, like ours, oxygen is very rare in the universe. If a planet is full of oxygen, there has to be life. So if by evidence of life you mean astronomical evidence, I think the answer is yes, because this telescope is going to be operational in 2027. If by evidence of life you mean somebody coming to us and talking to us, the answer I think is no.
Thank you, Paulo. We have another question here. Okay.
Relating to that. You showed the exoplanet discovery so far. There is a peak in 2015 that corresponds to Kepler, I guess. You show a graph? Yeah. Kepler, I think. Kepler. Okay. Yeah. But there are more missions now coming online and in space and all, so the number is going to go up amazingly. But as I tried to say earlier, we're moving now from discovery to characterization. So one thing is discovery, then one thing is looking at the atmosphere and seeing what they're made of. That's what we're trying to do now, which is much more complicated, of course, because there are faint things close to bright things. So you have a faint planet close to a bright star, and it's very hard to study it in detail. So we need things like big telescopes.
Have you ever found any similar universe to ours with the sun and habitable zone like ours?
Yeah. All this, the figure where I showed all these planets with funny names, we know many now, which they call them Earth-like. So they have planets with masses similar to the Earth. The radius is similar to the Earth. They are close to stars similar to the Sun, and they are in the habitable zone. So there are many candidates. So if we had a good telescope now, we could zoom in on those and look for the biomarkers, they're called. So sign that there is some sort of biology going on there. Yeah, I didn't take any sides there. It's still, to me, it's still open. Yeah. There's no agreement.
So the other Facebook question is it possible we are like a second all black? Imagine everything you have explained before and scientists predicted already happened and restarted with the Big Bang.
Sorry, I missed the question. Sorry, can you repeat?
She asks is it possible that now we have a second all black moment?
Like a recycling of the universe.
Yes, something like that.
Okay. From what we know now, no. Because right now the universe is expanding exponentially, so everything is getting pulled away. And in the 70s there was this idea that there could be the universe could reach a certain size and then recollapse. At the moment, this is not supported by the evidence.
Thanks very much again, Paulo.
Sure.
As I mentioned, you all are supposed to be observing stars now, but only you can observe at the moment are clouds. So at least that was what happened 2 minutes ago. So I'll check again. But if not, we'll try again on Wednesday. If it doesn't work, we'll try again on Friday. And if it doesn't work, we'll try again some other time.